Hello. Wanted to let you know that I've come up with a new lab for you to do. And so when you go to Canvas, you're going to go to Modules and then Labs, and it's the Unit 1 Labs. Then when you open that up down at the bottom, you're going to click on the tab that says 1.9 Rotational Newton's Second Law. And then when you open up that document, you are going to do the pre-lab. But what I'm going to do is we're going to do the concept introduction together. And then I'm going to show you how to use the computer simulation that you're going to use to do the lab. So if you go down to the concept introduction, it starts off by talking about Newton's second law of motion. So you should already know that for systems that are moving sideways. So we say that this is the linear version of Newton's second law. Force equals ma. So a force causes a mass to move sideways. So that's Newton's second law for linear systems. But what we want to study today is Newton's second law for rotational systems. So the formula is similar in that it says that torque, and we use the Greek letter T, tau, to abbreviate torque. So a torque causes a object to rotate with a angular acceleration. So a linear acceleration makes something speed up or slow down in a straight line, whereas an angular acceleration makes something speed up or slow down when it's spinning. So the formula is tau is equal to I times alpha. So then the question is, what's this I thing? Okay, that's going to be called the moment of inertia, and it is the resistance that an object has either to be sped up or to slow down. So if something has a large moment of inertia, it's going to be hard to get it to spin. But once you do get it to spin, it's going to be hard to slow it back down again, the larger its moment of inertia. Okay, so let's talk about torque first. Torque is the letter tau, the T-shaped thing, and a torque is a twist. So if you got a ketchup bottle and you want to get the lid off of it, then you need to twist the lid off, or you're applying a torque to the lid. Torque is equal to the radius times a force. So if you look at that picture underneath it, it's a picture of a wrench, and then in order to get that nut off, you apply a force to the end of the handle. So the handle has a length R, you apply a force F to the edge of the handle, and then that applies the torque, or the twist, that loosens the nut. So in today's lab, you're going to be calculating the torque on the system. Okay, scroll on down a little bit to where it talks about the moment of inertia. So we mentioned that the moment of inertia I is the resistance that an object has to movement. The larger its I, the harder it's going to be to get it to move, and once it's moving, the harder it's going to be to stop it from moving. So it also depends on mass. So just like force equals ma, the I does depend on the mass of the object. So the bigger the object, the more mass of the object, the harder it's going to be to get it to spin. But it also depends on the shape of the object. And so, for example, think about trying to spin a ball, or what about trying to spin a rectangular object like a remote control? So this would have a different moment of inertia than a ball would be because it has a different shape. It also depends on how you spin it. So this thing, you could spin it like this, so that would have a moment of inertia, but it would have a different moment of inertia if you spun it like this. So it depends on how you spin it as well. And it depends on the shape. So it depends on the shape, depends on the size. So a larger object is going to be harder to spin than a little object, and then it depends on the mass. So we're only going to be looking at two objects. So we're going to look at a ball that is solid, and we're going to look at a ball that's hollow. And so I gave you the moments of inertia for those two objects. So the moment of inertia for the hollow ball is 2/3 mr squared. And then the moment of inertia for the solid ball is 2/5 mr squared. So you're going to need those two formulas when you do the lab for today. Okay, so now we're going to go down to the actual procedure. So it says to go to the simulation, rotational inertial, and it's found at that particular website. So I would do a cut and paste. So cut that HTTPS thing and then paste it into your browser, and it will take you to the website. So the website is, let me see if I can. The website is called O Physics Interactive Simulations, and it's rotational inertia and torque. Okay, so hopefully you open that up as well. So you're listening to me, and then maybe you got a split screen where you can be looking at the simulation, and at the same time you can be looking at the lab. Okay, so you're going to go down to part 1, and it says to click on the box that says solid sphere. So for our first experiment, we're going to use the solid ball. And it says to set the radius to a particular radius. Now I'm having real problems because my computer screen is too small and I'm trying to look at 3 things at once here. So you're setting the radius to 2 meters. You are going to set the mass to 10 kilograms. So either type it in the box or use the slider for that. And then you are going to calculate the moment of inertia. So I gave you the formula for the moment of inertia I for a solid sphere, so plug those numbers into it and calculate its moment of inertia. Alright, then set the force equal to 20 newtons. That's the force that's going to cause that ball to spin. And then press the start button, and then it will start to pull down on that ball and it will start to spin. Now I want you to note the rate at which it begins to spin. So on some of these it's going to very, very slowly begins to spin and then it speeds up, whereas other ones it's going to speed up very quickly. So that's related to the angular acceleration, and you want to see how do they spin depending on its moment of inertia, and you should be able to see a relationship between them. Then once you've done that, you're going to answer the questions. So there are 4 questions that you need to answer based on your observations of that experiment. Okay, I will be right back, and I'm going to take a break, and when we come back we're going to do part 2 of the lab.